Okay, Assalamualaikum dan salam sejahtera. So we continue our lesson about boundary layer. But now I would like to discuss with you, to share with you the idea of what happened if laminar boundary layer cannot be neglected from the situation. Because in previous lecture, we say that we could use power law, or even we could use empirical form if the condition is fully turbulent or 100% turbulent. But sometimes, okay, in real situation, we found that laminar boundary layer is also dominant. Okay, what happened? Okay, let's say the example that we used in last lecture, maybe the plate is too long, 40 meters sometimes, and then all the velocity is too high, 30 meters per second is quite high. That's why the boundary layer is 100% turbulent, and then we could solve using that idea. But if the velocity is not too slow but not too high, so it's in intermediate range, it will create about a laminar boundary layer for certain length. Then the transition occurs, and then it will create turbulent boundary layer. So in this situation, we cannot neglect the laminar boundary layer here because the length of laminar boundary layer is quite dominant. It's from this picture, you could see that the laminar boundary layer is maybe 1/3 of the total length. So mean 1/3 of the total length is 33%. So means that you cannot neglect the existence of laminar boundary layer. So which one? How to solve this problem? Are we going to use 100% laminar or 100% turbulent? Oh, we need to do something to make sure that the laminar boundary layer effect is counted in this situation. Okay, so for condition number 3, we try to solve problem where the laminar boundary layer cannot be neglected in the situation. Okay, to simplify this one, I think it is better for me to use example. So you could get this example in page 394 in Porter textbooks. Estimate the boundary layer thickness at the end of 4-meter long flat surface if the air free stream velocity is u equal to 5 meters per second, and predict the drag force if the surface is 5 meters wide. So the question asks you to calculate the boundary layer thickness and the force if the laminar boundary layer is neglected. So mean we assume that it is 100% turbulent. So and then we need to calculate the laminar boundary layer using the Reynolds critical. So Reynolds critical here means the borderline between laminar and turbulent boundary layer. So this is the number 5 times 10 to the power of 5. So so this is the basic idea. Previously, in our tutorial, we will use velocity profile to determine the boundary layer. So however, in this situation, in this question, you don't know what is your velocity profile. If you don't know your velocity profile, it is okay. So it is okay for you to use this assumption. So for laminar boundary layer, it is okay for you to take Blasius exact solution. So mean the delta and the CD, you could take Blasius solution, means the value that's calculated from the Blasius exact solution as your representative. So normally we call that Blasius exact solution is the representative for laminar boundary layer. And then for turbulent boundary layer, it is okay for you to take 1/7 power law. So what is 1/7 power law? So as I said, U over U for turbulent can be written as 1 over delta with the power of 1 over n. But normally the turbulent is started with 1 over 7. This is the common turbulent condition that are found in a normal situation. So that's why in some textbook they will call that the 1/7 power law is the representative for the turbulent boundary layer. So in this situation, because we don't know the velocity profile, it's not given in the question. So we could say that our laminar boundary layer can be calculated by using Blasius exact solution here, and the turbulent boundary layer can be used the idea of 1/7 power law. Okay, so we speed up our calculation because we already know about the laminar, we already know about Blasius, we already know about the turbulent and 1/7 power law. Okay, so we try to answer A condition, which is laminar boundary layer will be neglected. So we calculate the Reynolds number at the edge of the plate. So at the edge of the plate means at the end of the plate here. Okay, this is the starting point and this is the end point. So we substitute the value. So please remember we could calculate Reynolds number whether you are using kinematic viscosity or dynamic viscosity. So we substitute the value and then we get it is 1.25 times 10 to the power of 6. So and then we found that 1.25 times 10 to the power of 6 is larger compared to the 5 times 10 to the power of 5, means the boundary between laminar and turbulent. So now it is confirmed that the at the end here it is in turbulent boundary layer. So and then as I said, we just use the value of delta from 1/7 power law. You could refer this to any textbook or you just refer my previous notes. So we discussed about how to get the value of delta from 1/7 power law. So and then we substitute the value of length for Reynolds number here. So we get delta is 0.0917. So and then we could calculate the drag force by using this equation, and this the value of CD here is also calculated in previous notes. Okay, we substitute the value, so we get it is 1.28 Newton. So this is the value of CD. So this is the value of delta and CD if we assume the boundary layer is 100% turbulent. So we neglect the laminar boundary layer. Okay, let's say we solve a B situation where the laminar boundary layer is accounted. So, okay, before we make any decision here, whether we want to take laminar boundary layer in our calculation or not, actually, we must know what is the length of laminar boundary layer. So, how to calculate the length of laminar boundary layer? So the idea is simple. So we have a flat plate like this. So we have a boundary layer like this. So and then we know that, okay, the molecule flow from left to right in laminar, and then at certain point, so it will become turbulent. So this point is actually the critical Reynolds critical. And Reynolds critical here, normally, if not given, you may take it is equal to 5 times 10 to the power of 5. So we will use this idea, this Reynolds critical. Okay, we could know the value of this length. Okay, the value, the length here. So means we reverse the calculation. We know the Reynolds number is 5 times 10 to the power of 5. So and then it is equal to rho ux over mu. So then we could calculate the value of x here. So it is equal to 1.6 meter. So and then if the length is 1.6 meter over 4 meter, means the total length of plate is 4 meter, and 1.6 is laminar boundary layer. So mean laminar boundary layer shows around 40% from the whole plate. So means that 40% is a big number, is a big portion. So means that actually we cannot neglect the existence of laminar boundary layer. We need to take into account the effect from the laminar boundary layer. Okay, so this is our judgment because normally if you calculate the laminar boundary layer is less than 10%, it is okay for you to neglect the effect of laminar boundary layer. But if the laminar boundary layer is more than 10%, means that you must calculate the laminar boundary layer with the turbulent boundary layer. Okay, so and then first, we need to determine the thickness of the boundary layer at the end of the laminar boundary layer. So because in this situation, the laminar boundary layer is not given, the velocity profile is not given, so we assume that the delta here can be calculated by using the Blasius solution. So the Blasius given as 5x over square root re naught, so it is equal to 0.0113 meters. So and then okay, from the 1/7 power law, so the turbulent boundary layer thickness is given by 0.38x over Reynolds number to the power of 1.5, 1 over 5. So, and then we need to substitute the value of delta here, okay, with this value, because we want to calculate the value of x here. So, and then we found it is equal to 0.292 meter. Okay, actually, what is the meaning of this calculation, this page calculation? So the meaning is, okay, we could see like this. I think I use this page, it's better. Okay, so we have laminar boundary layer here. So it's moving here. And then at the boundary, so we calculate this is, the length here is 1.4 meters. Last time we calculate it is equal to 1.4. Okay. Okay, so at this point, actually, both boundary layer share a same thickness. So thickness, ketebalan di sini kita kata dipunyai oleh kedua-dua keadaan. Turbulent boundary layers and laminar boundary layers is actually sharing the same thickness at this point. So the thickness at this point, we could calculate it as this one. Okay, we could calculate it as this one, 0.0113. Okay. Okay, so this is 0 point. So the thickness here is 0.00113. So and then, but we need to calculate what is the delta, what is the x prime here. So what is x prime? So x prime here is the starting point for the turbulent boundary layer. Okay, please remember at this situation, okay, at this thickness, okay, the turbulent is already occur. Okay, this is the transition. Okay, this is 100% laminar. Okay, and then in the transition, okay, there are percentage. So here is maybe 30%, 70% laminar and 30% turbulent. And then this is the percentage of laminar is become smaller and smaller, and then the percentage of turbulent is become bigger and bigger. And then at this point, it is 100% turbulent. Okay, so we need to calculate, we need to estimate. So what is the starting point of the turbulent boundary layer here? Why we need to know the starting point of turbulent boundary layer? So it is because according to our theoretical, so please refer back to turbulent boundary layers theoretical. So we start with x equal to 0. So means that the theoretical of turbulent boundary layer is start at x equal to 0. But according to this situation, okay, we don't know what is the x equal to 0. So we could calculate it by knowing the value of delta here, and then we recalculate the value of x by using the turbulent boundary layer. That's why in this calculation, first we calculate the delta, the boundary layer thickness, by using the laminar, because we know the starting point of laminar boundary layer. because, and then at critical real number, mean at x equal 5 times 10 to the power of 5. So means we know the real number. Okay, the delta here is actually same value with this delta. So means we know the real number critical, 5 times 10 to the power of 5. So the delta here is this one, means that we could calculate the value of x. So what is this x? So this x is equal to 0.292, and the value of 292 here is actually represent the starting point of turbulent boundary layer. So the distance here is 0.292. Okay, then what we need to calculate here is we need to calculate the total length of turbulent boundary layer. Okay, so here we could calculate the turbulent length, the length of turbulent boundary layer by, so we know the total length here is 4 meters. And then we know that the laminar only length is 1.4. So, and then we know that here the starting point is actually 0.292 to the left. So means that I think by simple mathematics, we could calculate the total length of turbulent boundary layer by using this equation. So we have the total flat plate length, we minus with the total laminar length, and then we add with the length here, mean length from the critical to the starting point of turbulent boundary layer. So if we do that, we could say that the total length of turbulent boundary layer is equal to 2.69 meter. So now, when we calculate the value from turbulent boundary layer, so we need to use this length. We cannot use 4 meter. Kita tidak boleh menggunakan 4 meter kerana apa? Kerana kita ingin mengira turbulent boundary layer, dan turbulent boundary layer hanya berlaku daripada kosong hingga akhir itu sepanjang 2.69 meter sahaja. Oleh itu kita tidak akan menggunakan 4 meter. So this value, this length is very critical. You need to get it because here in laminar or turbulent theoretical, okay, we develop their equation by assuming boundary layer starts at x equal to 0 and delta equal to 0. So this is the basic idea in development of boundary layer equation. So that's why we need to know what is the starting point of turbulent boundary layer. Okay, so let's say we know that the x is 2.69, and then we need to calculate what is the Reynolds number, the total Reynolds number. So we substitute with 2.69, so we get it is 880. So and then we could calculate the delta is 0.0668 meter. So we found that this is actually the final boundary layer thickness that occur in that situation. So means that here, okay, in previous calculation, if we assume it is 100% turbulent, mean we neglect the value of laminar boundary layer, so maybe the thickness is a little bit thicker because we assume from the starting point here, the turbulent occur. But if we assume that turbulent only occur at this starting point, so means that the delta here, the boundary layer thickness is a little bit thinner. So means that the value of delta here can be calculated by using the turbulent boundary layer, but we use the length of turbulent boundary layer only 2.69. So we cannot use the value of 4.0 meter. So from this calculation, we get 0.0668 meter. So if we compare from the previous answer, if we not neglect the value of laminar, so it is 0.091 meter. So means that the previous calculation is 37% higher compared to the second calculation. So and then for the drag force, okay, so and then for the drag force, we know that the Reynolds number is, if we substitute the value here, so the 4 meter here, it is equal to 1.25 times 10 to the power of 6. And then we need to calculate the value of CD by using this equation. Okay. At this point, please remember this equation. Okay, and then we get 0.0034304. So, and then we substitute into this equation. I think this equation is familiar right now. So we substitute the value of CD as 0.00304. And this is the area of the plate. This is the speed. And you will get it is equal to 0.885 newtons. Okay, the problem is here why we use this value. Okay, so this value is actually come from this guideline. Okay, we know that actually we not 100% calculate using the idea of turbulent boundary layer. We need to subtract a little bit. So that's why all this equation has minus of something, minus of 1,000, 1,700, 2,000. Why we need to subtract with certain value? Because we are now, okay, if we calculate 100% of turbulent, okay, we actually make a false area here. So this area is actually not exist. That's why the value is extremely large, the error. Okay, and then if we calculate the value of turbulent boundary layer, so means that the idea is we assume that we calculate the total turbulent boundary layer here, then we need to deduct, we need to minus with this area. So this is conducted using experimental and also numerical. So what we could use here is, I hope you could remember this table. So means that if the Reynolds critical is 3 times 10 to the power of 5, and then you could have this Reynolds number. If the Reynolds critical is here, you could have this one. And if the Reynolds critical is 6 to the power of 10 to the 5, so you could use this CD. So according to this, we are using this one. So we are minus this value. Okay,